Okay, we are going to do the second part of Volumes of Revolution. And so this Volumes of Revolution disk method, part 2. By the way, I'm going to go away from any color pen other than black because it doesn't seem like it shows up very well unless we run into an emergency and I don't have any other color pens. The only difference between this, what I'm going to show you now, and what I showed you before is before we had actually kind of an unusual situation. And that was that we were always revolving around the x-axis. Well, what happens if we're not revolving around the x-axis? There's actually two parts to this as well. What happens if we're going around the y-axis versus what happens if we're just going around some other horizontal axis. So for instance, let's say that I told you that I have this curve. Again, I'm going to do this conceptually. This curve. And we're going to do the area between it, so f of x, between f of x, x equals a, x equals b, and y is equal to c. So there's some line here, and we're going to take this, and we are going to revolve it around the line y is equal to c. So we're actually revolving it around here. Well, what's going to happen is before we just took f of x and went right down to the x-axis. But here, if you think about what's happening, we're actually making this little shape right here, something like this. And we're simply revolving it around that line. So what I need to do always, we started this last time, is figure out what would that radius be. Well, my radius here, my area is still going to be pi r squared, but my radius is f of x minus c, because this line was y is equal to c. And as a result, the answer for this, or the volume for this, would be from b to a, pi r squared, so pi would be out in front. This would be f of x minus c squared dx. So for instance, let's say we had y is equal to the square root of x, which is going to look like that, and the line y is equal to 1, which would look like this. By the way, they would hit right here at 1. Between x is equal to, let's do 2, and x is equal to 3. So it would be this right here. And it's this volume that's going to be formed by revolving it around the line y is equal to 1. So we're actually getting very similar to the shape that I just did, something like this. It's coming down like that. Okay, so how would I do it? Well, I'd have to, again, figure out what this would be. What is that radius right here? Well, this is square root of x. This is 1. So that r is the square root of x minus 1. And therefore, my volume will be from 3 to 2 square root of x minus 1 squared dx. I'm not going to work that out. You can do that on your calculator. The important part is setting it up, not getting the answer at this point. And I just want to show that to you. Now, that's one problem. That is when the rotation is actually touching where the area is touching the axis of rotation. What if it's not doing that? What if we had something like this, where we had these two? So we have f of x and g of x. And by the way, the fact that they're going to be squared means it doesn't really matter which one's on top or which one is below. I'll pull that forward a little bit. And let's say that we're going to go, let's do from where they meet, so from A to B, because that's very common. But we are going to revolve this around the line y is equal to c. Well, it's exactly what we did before, except that now I can't just use f of x as my radius, because we're not going around this line here, the axis. We're going around this line. So what is this distance right here? Well, this radius would be f of x minus c. And what is it that we are subtracting out? It's this radius. So I actually call this, they oftentimes will do this, big radius, little radius, is g of x minus c. And as a result, when we do this, pull this down just a bit, when we do this and put this in, this would be pi from b to a, f of x minus c squared, and subtract out from that g of x minus c squared, dx, and that would be our value. Basically is r squared minus little r squared. If you can figure out what the radius is from there, from one place to the other, and basically it'll be this each time. So let me show you a different problem, slightly different. Let's say that we had the same basic shape that I just did. Move this over so you can see it. Sorry about that. And we had that curve and this one, and this is f of x and g of x. But we are going to revolve this, and the area enclosed would be area enclosed by f of x and g of x around the line y is equal to c, but the difference is y is equal to c is up here. So basically we're revolving it around this way. Now you have to just stop and think. What's my big radius? Well, my big radius, by the way, this is what it comes down to right here. My big radius is that one right there. So how do I figure out what that is? Well, let me put some numbers in for you. I find that this helps. Let's say y here is 10. And this number right here is 4. What's this length? Well, it would be 6. But how did I do that? I took 10 minus, in this case, g of x would be my big radius. Or to make it more, c minus g of x. And my little r would be this distance here. I know I'm not right on top of it, but you get the idea. This distance. Let's say that this was 6, and again, this is 10. Well, then this distance here would be 4. But the way you did that is you went 10 minus 6. C minus f of x is my little r. And what we would then get is from b to a, or a to b, my volume would be pi from a to b, c minus g of x squared minus c minus f of x squared dx. Now,